Hey guys, welcome to Unit 4, which we start our study of work, energy, and power. And so we're starting off with work. And work is a quantity, it's an energy, right? We measure work using energy. And we define it as the transfer of energy from one body to another. And the math way to say that is work is equal to a change in energy, or the final energy in the system minus the initial energy in the system. That would be what the change in energy is, okay? We can calculate it, right? We have an equation. Work is the net force on the object times time, or distance, and we get a Newton meter. We call that a joule of energy, right? So we indicate that with a capital J here. That's a unit of energy. These are the same as torque, and remember torque is, remember that from 8th grade, but it's a distance to a pivot point, and we'll talk all about that when we talk about things rotating and that kind of thing. So the first example we have is something being done against gravity, or work against gravity. In other words, you're going to pick something up, right? That's kind of what we're doing here. So we have this object, we have a free body diagram here with the force of gravity, its weight, and then we are applying that force, well, the applied force pointing straight up. And so to move it at a constant velocity, we know that the applied force must equal the force of gravity, right? So work is going to be Fg times d, which is just the mass of the object times gravity times the distance we're lifting it up. And we get about 29.4 joules. That's how much work is required to lift up a 2 kilogram book, so that's roughly 4 pounds, from the floor to a height of 1.5 meters. So since the velocity is constant, the net force acting on the book is going to be 0. So F net is 0, or F net is 0, okay? So we have another way to look at it. So we're working on an object. We're holding the medicine ball still for 10 seconds, right? So once again, we have the same idea. We have the weight of the thing and then the force holding it up. So energy is being used on the object, right? But no work is being done on the ball, right? The distance it's being moved is 0 meters, right? Work is force times distance. Work is force times 0. So that's how we get that. So this is going to be 0 joules worth of work done on an object that you're just holding still. Okay? So the kind of problems we end up seeing a lot of the times are these forces at an angle, okay? So the first thing you do, we're going to draw this free body diagram. Always draw the picture, right? It helps us to visualize what's going on. We have the weight of the object, the Fg. We have the normal force pointing this way. It didn't tell us there wasn't friction, but we're going to assume there's some kind of friction here. And then we have our applied force. I'm just going to call that F. I know that there's some kind of F in the X direction, and there's some kind of Y direction here because of this angle. Breaking those apart to its components, this is F cosine theta, and then the Y is F sine theta. So if we need a refresher on that, let me know, we can fix that. And what's happening here is only the force in the direction of the movement, or the distance, is doing any kind of work. So work is going to be the force in the x times distance. So we're just going to plug that in, F cosine theta times distance. Plug in our numbers here, 35 newtons, a cosine of 40, and a distance of 20 meters gives me about 536 joules worth of energy done, okay? The vertical component, there's no work done in the vertical component because the distance in the y is 0 meters. So that's something to make sure we are aware of, right? Work in the x direction is distance in the x times the force in the x. Work in the y, kind of like what we had earlier, force in the y times distance in the y direction. So only in the direction are we going to use that. Okay, so we have another example here. So once again, do we use the net force or the applied force? Well, we're going to use the applied force. If the net force is 0, that simply means it's moving at a constant velocity. So now we're taking apart the thing and looking at individual forces. We know that work is force times distance. It looks like there's a 220 Newton force being applied here. There's a 15-meter distance. He's pushing the thing. So it looks like a 3,300 joule work done. So 3,300 joules worth of energy is done when working on this. So when finding the total work done on the object, we're going to use the applied force. Sometimes we're going to ask about the work done by friction and individual forces, and we'll talk a little bit about that when we talk about conservation of energy. But for now, we're going to use the applied force. That's how our problem sets are going to go. So this last chunk that we're going to talk about here is to scalar or not scalar. So work is the product of a scalar and a vector. Work is force times distance. The force being the vector, the distance is going to be the scalar, right? We're just looking at the distance it's traveling. Work is going to end up being a scalar quantity, but we can call that negative or positive. And what we mean by that is energy going into the system somehow, or is energy being taken away? So for example, friction is going to take energy away from the system. But if something is falling down or rolling down an incline, gravity tends to give it energy, right? So we'll use these 4 examples to frame our thinking here. The car accelerates from rest. Well, that's a positive energy or positive work done, right? We're giving that some energy. The skater stops suddenly, right? I've taken energy away. Now they're no longer moving. Lifting something over your head, I have to give the object energy to lift it up against gravity. And a ball rolling down a ramp. So remember we talked about how if I'm at an incline, the object is doing this with his FG. This piece right here, this FG parallel, is the component of weight giving it energy down the ramp, okay? So that's why it's going to give it energy. It's not moving and then it is moving. So that's how we're going to frame our thinking on that. All right, let me know if you have any questions. Good luck on your problem sets. I'll talk to you later. Bye.